Hello guys, you're welcome to this lesson. In this lesson, we'll be looking at how to balance nuclear reaction. How to balance nuclear reaction. So, anytime you're given a question to balance any nuclear reaction, it just follows the same ideology in balancing chemical reaction. That is, mass is always conserved. Is that okay? But in nuclear reaction, it deals with both the mass number and also the atomic number. So in balancing nuclear reaction, the mass numbers of all the reactants must be the same for the mass numbers for all the products. And also the atomic numbers for all the reactants must be the same for the atomic numbers of all the products as well. It simply means that when you add all the mass numbers of the reactant, it should be equal to the total sum of the mass numbers in a product. And if you add all the atomic numbers of the reactant, it should be equal to the summation of all the atomic numbers in the product as well. That is how we balance nuclear reaction. So I have some examples here. We will go through them one after the other. So we have to balance the following nuclear reactions and identify X if possible. So in the first one I have PO with a mass number of 212 and a proton number of 84 goes into PB with a mass of 208 and then a proton of 82 plus a certain X which has a mass of A and then a proton of B. So in order to balance this nuclear reaction, when we add the total masses of the products, the species in the products, it should give us the total mass of the reactant. And also, considering the total atomic number here should be equal to the total sum of the individual atomic numbers here as well. Is that okay? Alright, so now let's go through. So in the first one, we equate the masses together. This must be equal to the addition of this and then this. Is that okay? So for A, we say 212 should be equal to 208 plus A. That is for the mass number. Is that okay? So over here, we have a linear equation. We make A the subject. So 212 minus 208 will be equal to A. So therefore, A will be equal to what? 4. Is that okay? So it means that our A here is 4. Our A here is 4. Is that okay? So to balance nuclear reactions, we have to make sure that the mass numbers are the same on both sides of the equation. The total sum of the mass numbers for the reactant should be equal to the total sum of mass numbers of the product. Now let's come to B, that is atomic number. So the total atomic number of the reactant is 84. So we can see that 84 must be equal to 82 plus that of B. So over here we have a linear equation, we just find B. So 84 minus 82 is equal to B. Therefore B will be equal to what? 2. It means that our value for B here is 2. Now, to validate our ideology, we have to make sure that once we add the masses on the product, it should be equal to that of what? The reactant. So here we have a total mass of 212. Now let's come here. We have 208 plus 4, and that is what? 212. So the mass numbers are the same. Is that okay? Now we have a total proton of 84, and then here we have 82 plus 2, and that is also equal to what? 84. Is that okay? So the equation is balanced. Is that okay? And now which particle here? This can be a helium atom or it can be an alpha particle. So since we have polonium undergoing disintegration, this is an alpha particle. Is that okay? Alright. So we can say that X here is an alpha particle which is emitted after the disintegration. Now let's move to the second one. So we have 137 for the mass number and 55 for the proton number. In total, we have only one reactant here. In the product, we have two species. We have BA and then X. BA has a mass of 137 and then a proton of 56. We don't know the mass and then proton of X. Is that okay? So we calculate that as well. How do we get that? The same ideology. So for B, we are considering the mass numbers first. So 137 should be exactly equal to 137 plus C. So we have a linear equation again, we just mix the subject. So 137 minus 137 is equal to C. Therefore, C is equal to what? 0. So our value for C here is 0. Is that okay? Now let's move on to the proton number. So with atomic number 2, we have 55 must be equal to 56 plus D. So we just make D the subject. We have 55 minus 56, and that is equal to D. Therefore, D will be equal to what? Minus 1. So it means that our value for D here is also minus 1. So our X becomes 0 minus 1. Is that okay? 0 minus 1. Or let me write it here. Here is 0, and then here is minus 1. So to validate our ideology again, we have to check the total. Here the total mass is 137 plus 0, that is 137. And the total mass here is 137, so it is balanced. Here the total proton number is 55. Here is 56 minus 1, and that is 55. So it is also balanced. Is that okay? So that is how we balance nuclear reactions. Let's solve for the remaining ones as well. So we have C. In example C, we have a total mass of 78 in the reactant, should be exactly equal to 0 plus E. Is that okay? So 78 minus 0 is equal to E. Therefore, E is equal to what? 78. Is that okay? Our E is equal to 78 for our third example. Now let's calculate for the proton atomic number. We have a total of 33 in the reactant, and this should be exactly equal to that of negative 1 plus F. So how do we get F? So we just make F the subject, that's 33 plus 1, and that is equal to F. So therefore F is equal to what? 34. So here F is 34, and then E was 78. Now let's check whether it is correct. The total, we have only one species in the reactant. The total mass number is 78. And then here we have 0 plus 78, it's still 78. So the mass number is balanced. The proton is 33 in total. We have only one. Here we have negative 1 plus 34, and that is 33. So it is also balanced as well. Is that okay? Now let's look at the third example, the fourth example, sorry. In the fourth example, we have this plus this. So we have two reactants and then two products. Is that okay? So let's consider the mass of the reactant first. So the total mass of the reactant is 12 plus, please, the 2 in front of the particle here, that is a neutron here, affects both the mass number and then the atomic number. Is that okay? Very good. So the total mass for the first one becomes 12 plus 2. And this should be equal to 14 plus G. Is that okay? Now how do we get G? So we have 14 is equal to 14 plus G. So 14 minus 14 is equal to G. Therefore G is equal to what? 0. Or G will be equal to 0. So it means the value for G here is 0. Now let's calculate for the atomic number, that is the H variable here. So we have 6 plus 2 times 0, and that is 0. And this must be exactly equal to 7 plus H. So 6 is equal to 7 plus H. So 6 minus 7 is equal to H. Therefore H will be equal to minus 1. So it means that our value for H here is minus 1. Is that okay? So we can rewrite it here. Our G is 0, and then our H is minus 1. Now let's check whether it is balanced. So we have a total of 12 mass here plus 2 times 1. That is 2. So a total of what? 14. Now let's look at the total mass we have here. We have 14 plus 0. That is 14. So the mass number is what? Balanced. Now let's consider the proton number. We have a total of 6 here plus 2 multiplying the mass atomic number here. That is 0. So 2 times 0 is 0. So we have a total of what? 6. Now let's come here. We have 7 minus 1, and that is what? 6. So the proton number is also balanced. Is that okay? Now let's consider our last example. So in the last example we have two reactants, and then also we have two products. Is that okay? And we are asked to balance this equation. We have some variables that we need to calculate for them as well. Is that okay? So the total mass number for the reactant is 19 plus y, and this should be exactly equal to the total mass number of the product. That is 20 plus 0. Is that okay? So now we have a linear equation. We calculate for y. So 19 plus y will be equal to 20. That is 20 plus 0 is 20. So y would now be equal to 20 minus 19. So y will be equal to what? 1. Is that okay? So our y here is 1. Now let's calculate for our z. So the total proton number for the reactant is 9 plus z. And this should be equal to 10 plus negative 1. 10 plus minus 1. So we have 9 plus z is equal to 9. So our z will be equal to 9 minus 9. So z will be equal to what? 0. Is that okay? Z will be equal to 0. So it means that our value for z here is 0. Now let's put it into, let's represent it here. So here is 1, and then here is 0. And let's do the calculation whether the equation is balanced. So let's consider the mass numbers first. The total mass number is 19 plus 1 for the reactant, that is 20. And then here we have 20 plus 0. So the mass numbers are balanced. Now let's consider the total number. We have 9 plus 0, that is a total of 9 here. And then we have 10 minus 1, that is equal to what? 9. So the mass is also balanced. So in balancing nuclear reaction, it just follows the same ideology in balancing chemical reaction. Mass is conserved for chemical reaction. Is that okay? So for chemical reaction, it is just a rearrangement of atoms and molecules. So nothing changes. The mass is still the same regardless. For nuclear reaction, the mass numbers must also be conserved. And then also the proton numbers must also be conserved. Is that okay? So in balancing nuclear reaction, you have to make sure that the total mass numbers of the reactants must be equal to the total mass numbers of the product. Same applies to the total atomic numbers for the reactant must be the same as the total atomic numbers for the product as well. Now let's move on to the next aspect, the shortened notation for nuclear reaction.